We're still in bed, it seems like. But anyway, we have two interesting talks by two experts in the field of epidemic modeling this morning session. And the first one is Greg, who will talk about Greg Rempala, who will talk about survival models and connecting them to epidemics one way or another. The floor is yours.
Yeah, thank you so much. This is a great honor to be here, and I really appreciate the invitation and the opportunity to listen to some excellent talks and also share some of the work that we've done. So I've been involved in various aspects of epidemic modeling, but today I would like to talk specifically about one type of idea that's deeply related to estimation of parameters and some kind of statistical approach. So COVID is a complicated and has been, a major event that we have looked at from various angles. I will not really talk about COVID. There's lots of people who can do this much better than I can. But I just want to acknowledge that at least some of the ideas that I will try to explain came as a result of a necessity of making some kind of conclusions about data that was pouring in, and various people making various comments which sometimes didn't make much sense and needed to be addressed. So this was a kind of general motivation. So, I'm a mathematician, but for about a year, I was involved with this group in the state of Ohio. This was called the Governor's Special Task Force on COVID. And I was along with my colleague from the math department, who was the real epidemiologist on that. We were basically in charge of trying to give governors some ideas what's going to happen. And I, up until now, I remember the first day when they basically asked us to run a model and tell them, how many cases are we going to see next week? This was in March. So, we basically ran some kind of model that the best one that we could put together on a very short notice. And then I couldn't sleep the entire night because, I made a prediction. I basically said it's going to be X people. And then, I knew, unlike many of my math papers, the people will verify that claim very quickly, probably by tomorrow. And so it was very stressful. But it actually turned out that it was not bad. And for about a year, we were involved deeply with some of the works of the Ohio. Ohio actually did quite well, at least initially, up until the politics sort of started to raise its head, and it became, more of a political exercise in the sense that there were lots of external pressures on various types of policy. So this is kind of a background for what I would like to talk about. But in principle, I would like to talk about some of the underlying mathematical ideas that came out of some of these interactions. So the person up here, this is the health director, so she was like the Minister of Health in Ohio. And this is the governor who was showing our model. For some reason, he told his people to make him a different picture. So, we had a very nice one, and then he came up with this really ugly one that he was showing at the press conference. But anyway, the calculations were ours. And for a while, basically until January 2021, we were sort of involved with trying to give some ideas about what might happen, what are the prognostics for Ohio, etc. And the model that we used was a network model, which has all sorts of additional assumptions. But again, I will not talk about it. The reason that we're able to build such a complicated model and actually feed it data and estimate parameters is because of these survival models. So I will talk about survival models today in the context of epidemic. So let me start with a very simple example. And in fact, I will use the simplest possible epidemic model and SIR model throughout, because it really doesn't matter. And it makes things simpler. I will look at the simplest possible case, meaning I will look at the Markovian system. So in the stochastic SIR model in general, I have three types of molecules, as we all know. And the idea is that I will have two types of reactions. If I think about it from the point of view of a chemical reaction system, then I have these S IR type of molecules, and there are two reactions. One is the infection, and the other one is recovery. And again, for simplicity, I am assuming law of mass action. So basically, I'm assuming that the rate of these reactions are driven by the appropriate polynomials in the numbers of molecules. The basic reproduction number is in this simple model typically defined as just as the ratio of the constant. So let's take a look at this model more closely. This is one of the probably best known stochastic model for epidemics. There is a standard Markovian algorithm for estimating parameters. There is a standard classical statistical theory for writing out the sort of Radon-Nikodym derivative, therefore the likelihood function, and basically fitting these types of models either in this setting or in more general compartmental setting. But I would like to look at this model from a slightly different perspective in a moment. And this model is what I would call an ecological model, in the sense that it really looks at the aggregates of these different types of molecules. Okay. So in a sense, you can think about epidemic models as being sort of divided into these two types, the ecological models and the agent-based. Agent-based are useful for some purposes. Ecological models are typically simpler, and potentially they can be more easily analyzed using standard statistical methods. Agent-based models are typically difficult to calibrate, and in general, these are typically very heavily based on simulation. So the idea here that we had was, on the other hand, maybe one more comment. Agent-based models are useful in some sense because they're really allowing you to look at the level of an individual. And the individuals are typically the ones that you will be able to sample. So you cannot sample typically an average of a population, that's difficult. But you can sample individuals. So you would get these statistical samples that somehow you would like to then be able to relate to some large computer simulation. It's generally difficult. So the idea here is that perhaps there is a way of trying to build these agent-based models in such a way that you could borrow some of the strength from the ecological model. So use ecological model as a way of simplifying your agent-based model, and then use that to make some inferences, for instance, or try to understand the dynamics of a particular epidemic. So my favorite construction, as I was telling earlier, Etienne, I think that this is my favorite construction in all of the stochastic epidemic models, the Selke construction. The Selke construction is really an alternative to a Gillespie algorithm, to the standard Markovian way of simulating a continuous time discrete state space Markov process. In fact, the Selke construction does not require this process to be Markovian, but for the sake of simplicity, and in order to be able to basically quickly skip over some things that I would like to talk about, I will assume for now that I'm just looking at the Markov process. So the way in which you create the Selke construction is as follows. You basically start with an individual who is initially susceptible, and you give that individual a random variable, a realized random variable. In this case, I will, just for simplicity, I will take it to be exponential with rate 1. And I will supply that random variable to every initially susceptible individual. And then I will initially have each one gets its own realization, right? So these are IID variables exponential, right? I will call it a threshold. And then basically I will look at the number of infected individual at time 0, the I of t. This is the number of infected, and I will compute this quantity. I will basically take some kind of scaled version of beta, which I will call a transmission rate. Let's say that my population size is n, so beta over n. And then I will take an integral over the total number of infected individuals. Okay, so the number of infected individuals over time, this is like the amount of infection that I have in my system, cumulative amount of infection. So no wonder this is called the cumulative hazard. Right, so this is a cumulative hazard function. The interesting thing is this cumulative hazard is random. That's the feature of the stochastic epidemic model. And that's also what makes it different from sort of standard statistical theory of survival analysis. In statistical theory, typically you would assume that your hazard function is non-random. So this is a cumulative infectious pressure. And the idea of the Selke construction, the crux of the Selke construction is now you will compare this threshold with your cumulative infectious pressure. So basically you will look for a time at which for a given individual with the threshold Q, that threshold drops below the cumulative hazard. And at this time, you will basically switch this individual status from S to I.
N is the number of susceptibles, or
N is some scaling. I can assume I will send it to infinity. So you can think about it as yes, the number of susceptibles or the total number of the population, total size of the population. It's a number that it's assumed to be large. And this basically means that somehow overall infection rate is controlled, right? So this beta over N is meant to give you some control over overall infection in the entire population.
Is it equivalent to using the standard instance rather than mass action instance?
Yeah, I think so. That's right. That's exactly. I think that's right. But you know, the point here is that you know the overall infectiousness is beta. It's not. It doesn't depend on the size of your population.
So should I think of An of t starting really at the time it's not adapted to an infection? An of t is just the amount of infection in the population.
Correct. Exactly.
Now your Q, shouldn't I start my Q at the time I get infected? Because otherwise
No. Q is not, you know, Q doesn't depend on time, right? Q is basically this exponential random variable. And you are defining the time of first entry in the world, right? So basically you're looking at the timing at which this An of t, which is a function of time, will go above this random threshold. I will show it in a moment in an example. But whenever, now the one last thing about the Selke construction, if I will now assume that these infected individuals recover at some exponential, according to some exponential random variable, then I basically have the standard Markov model. But in fact, in the sort of obvious Selke construction, you don't need that assumption. But here I will make it. So basically the way that this works is you have, let's say that I have a population that had only 3 individuals in it, Q1, Q2, Q3, those would be order statistics. So I order these random quantities according to their magnitude, this the first, the second, the third, and I start basically what this graph is doing, it's basically drawing that particular cumulative function from time 0. So basically I have, let's say, initially only 1 infected. So then this basically looks like t times beta over n, right? So this is just a linear function. It runs like this. At some point, it reaches the first threshold, at which point I will have 2 people and I will change the slope. So you see that basically this is a piecewise linear function with different slope. At some point, people will start recovering, meaning that I will change the number of infected. So then the slope will change. At some point, I may run out of infected, at which case this will stabilize and this will no longer continue upward. If there is any Qs left above the threshold, those would be the survivors. So it's a very simple, very natural and easy way of doing exactly what? Basically generating a random variable from a random cumulative hazard. So the probability that this random individual has not reached yet the infectious status is basically the probability that that individual's threshold at time t was still above An of t, given the history of the process, right, from the very beginning. So because Q was exponential, then I can rewrite this probability. So that probability can be written as, yet again, conditionally on A and T. This is e to the negative A and T, where A and T is the cumulative hazard. So all this is saying that somehow, you know, this EA and T is just the cumulative hazard for that survival function. So another way of saying this, if I now will introduce this random variable t, which is standing for time when individual gets infected. So I have a random individual with a threshold q, and I'm interested in the random time when this individual switches from S to I. So that's t. So that basically means that that t conditionally of A and t is basically given by that expression.
So beta is then integrated into the A, or should it be?
So say again.
Where's your beta, your rate?
Oh, the beta is in here, right? So beta.
Was beta times
Right. Beta, but beta is basically included into these A and T. So the Selke construction is basically a way of realizing these random hazards. Yeah.
So the way that we choose the exponential distribution is just to get the simplification to the.
We will get to this, but for now I'm just taking rate to be fixed. This makes this easier.
But it has to be exponential.
Right, because you would like to be able to I mean, if you could take different variable, but then it makes it more complicated. I mean, that's the simplest way to construct random hazard.
Excuse me. So I agree with your expression, so the point, but the first point, HT contains information on Q, doesn't it?
No, it does not. Because HT is only
whether the individual has.
So this is the process that's basically So this is the history of the entire process. So the Qs were independent of each other. Okay.
Yes, Qs are independent, but then they are ordered. In fact, they are ordered.
They are ordered, but if I'm looking
When you order them, they don't.
But if I'm looking at the single Q, it doesn't matter. As long as I'm looking at the single Q, I think the only thing that I need to know. Anyway, so let's move on. So how can we make this Selke construction simpler? A very simple, obvious simplification is as follows. We know from just the standard law of large numbers for Markov processes that if we scale our total number of infected, then we end up with the quantity which is deterministic in the loop. So basically, the idea here is that I can use this approximation. I can take I, the random quantity, I can divide it by n, and that, by the law of large numbers, should at some point when n is large approximate quantity which is deterministic. And in fact, I exactly know what this quantity is. It's a piece of a trajectory of the appropriate ODE in this case. Since my model is Markovian, then the limiting law will be based on an ordinary differential equation. This is the macro SIR model, the kind that Abba was talking about yesterday. So the idea here, and again, just to make things a little bit simpler, I am using the scaling. So I'm scaling things in such a way that I can use these types of initial conditions. So I scaled everything by the size. So the idea here is that I could just take this Selke construction and replace this random hazard by this limiting hazard. And then think about this in terms of just the regular law, of just the regular survival model in which my hazard would be no longer random, but it would follow this limiting expression. So to make this maybe even a little bit more explicit, I can rewrite this. I can partially solve the SIR model, and I can write it like this. So first of all, ST itself can be written in terms of that quantity, but this I recognize as my limiting approximation to the Selke construction. So this is, I will call it calligraphic AT. So this is exponential of negative calligraphic AT. Then I have this quantity iota, which can be represented this way. And then RT, which is again integral, so it can be written in terms of this calligraphic AT. So what do these things really tell me? So they tell me the following, that I can think from, at least intuitively from the discussion that we had, I can think about ST as a sort of survival function. It's a survival function because it basically gives me a way of defining a probability law by means of that limiting hazard. And as soon as I do this, then I basically see that, for instance, this quantity, now I can think about it kind of as about density, because if I put this raw term on the other side, I end up with negative integral s dot u e to the negative. This looks basically like a convolution of two density functions. One of them is exponential. The other one would be the density associated with the survival function. So then this I is basically a density function, which is a density of a random variable, which is a sum of two random variables. The first one would be given by this ST law, and the second one is exponential. So what it basically is just a sum of two variables. The first of them is telling you about the timing of your infection. The second one is telling you how long you stay infectious, exponential in our case. So then that density would be the density of recovery. Okay, and then this thing RT, this is just accumulated random hazard, so non-random hazard at this point. So in fact, if I go back and look at the curves for the SIR model, I have this interesting interpretation that I never thought about really earlier, that this is kind of a survival function. This you can think of as a cumulative hazard, this is R, and this one is a density, meaning that this is the density of infection. So in fact, that picture gives me a probability law that sort of average individual in infinite population should follow. Okay, that's a very simple, I would say, intuitive way of thinking about it. Not clear whether it's useful, right? But
the blue curve seems to go down to 0. Is that?
No, it doesn't. I mean, it stays because, you know, the blue curve is it's not a true survival function, right? Because you have some survivors at the end.
Yeah, that's
So
what I meant. To me, it looks like this particular figure is going down to 0, but it shouldn't. It shouldn't. It shouldn't. So you know, so this will be a survival function conditionally on you actually getting inside.
In particular, your red curve will drop below the blue one eventually.
It should go to 0.
Yes, because it will have to go to 0. That's
Yeah, but if you choose the beta a little bigger, then the blue curve would not.
I mean, this is just a regular SIR.
Yeah.
So however the geometry of this works, this was just an example. So I just want to say, I want to add one additional component here. So all of this is in a natural way, and I would say quite nicely fitting this work of Gabriela Gomez on frailty. She was basically discussing frailty models and a couple of her recent papers. And this was one of the big things in some of the discussions about COVID. So I did it here, the Selke construction, in a very simple way, but in fact, I could easily augment it by some additional random environment. So that the simple way to do this would be, I would assume that I have some additional random variable that's associated with every threshold. And I will just augment this to make it exponential, not with rate 1, but with some rate q, and q would follow some distribution. So then I can basically follow a very similar argument conditionally on x. I can write the adjusted Selke construction, and the cumulative hazard will look like this. If I take this to the limit, and if I use again the appropriate law of large numbers, I basically end up with something like here, which is a frailty model. So the frailty model is nice because it gives you a way of incorporating very simply heterogeneity in your population. So if your population is heterogeneous in terms of the differences in susceptibility to infection, which very often you would be interested in modeling, then all you need to do is really introduce this frailty model and put some kind of structure on that frailty in order to be able to adjust for it. And it really doesn't really change anything from what I just told you earlier. The whole idea works. So if you have frailty, then you have this infinite system of equations when at 0 you have some q of x, when q of x is either a density or a mass function. You basically then can write ST in terms of this frailty. And the beautiful thing here, I was showing it to Christian yesterday, is that this expression simply says that your ST is now a Laplace transform over frailty distribution evaluated at this cumulative hazard. Right? So basically I have smoothed out this ST distribution with this additional operator, which looks like the Laplace transformation.
Sorry. The second equation, the IT.
So the idea is that, so I have iota here.
Distribution of X come into play.
So the distribution of X doesn't, because basically X is this is all conditional, right? So this is integrated over dx. I'm assuming that this integral exists.
You're integrating over X.
Over X.
But X, wasn't that the frailties, wasn't there a distribution?
So there is a frailty, yes, there is a frailty at time 0. S0 of X has the initial condition Qx.
So
So-
I'm confused too. Shouldn't dx be the integral with respect to distribution of x?
No. No, because basically, you know, I'm only assuming that at 0 S0, that integral will exist, right? So at S0, I will have this Qx. So that's basically how.
Can you go back one slide? No. Yeah. So this random variable capital X.
Uh-huh.
Oh, sorry. Okay. So is Q the distribution of?
Yeah. So Qx, the frailty distribution is fixed. It doesn't. There's no dynamics on frailty.
Okay, that's fine. But so the Qx did that, and if you now move forward, what's a Qx?
So Qx is basically S0 of X, right? S0 of X. If I had S0 of X, this would be expectation of frailty. But now S is a decreasing function. It's continuous. So that integral exists. But it's, you know, it depends on time, right?
So I should think of is x times s. Oh, but that's xt.
X is basically a heterogeneity in a way of your initial population, and that heterogeneity propagates in this list. I is still the total number of infections.
I understand that. I just don't understand how to get that.
Okay, so
I
we
understand
can,
it intuitively.
we can discuss it offline. This is the I was happy that this is the formula from the Gomez state. So that's, you know, I was able to at least reconcile it. So what I really want to bring to your attention is this. So somehow this ST, the way that I had it before, it kind of it looks like this. This is e to the negative cumulative hazard. Once I introduce frailty, I am basically taking this over here. When I am integrating, I'm basically taking the Laplace transform of the frailty distribution. And now it turns out even more interestingly that if you take some of these frailty distributions to be exponential family, for instance, then this can be evaluated and it gives you a different differential equation, which are, for instance, if you take gamma, you get some, you basically get back the JTB papers, Gomez's formula. Anyway, but that's really just a side note here. I wanted to maybe try to explain a little bit more about how this works. And more importantly, I would like to also understand a little better what is the error of these approximations, right? I'm just making some approximation. I'm trying to make an intuitive argument. I would like to be able to measure how much this really makes the difference. So this is related to this idea of a transfer model of somehow DSA framework. And this DSA framework is possibly useful because it's a way now of thinking about epidemics in terms of transfer times, as opposed to counting individuals in the count process.
DSA stand for?
Oh, DSA. This is dynamical survival analysis. So we wanted to somehow, so the dynamical survival analysis basically means that you are writing some kind of dynamical system and you think about its solutions as defining probability law of certain types. That's all it means. We try to use different acronyms, but this DSA sort of seemed to have stuck. And the point here is that I am interested in transfer time. So I have this imaginary unit in infinite population. This unit could be of time S, I, and R. And I'm interested in the timings at which this unit moves from S to I and then necessarily into R. And yes, this probability that the unit, I called it T. Yeah, so this is the time at which the unit became I. The probability that this time of infection is greater than T is basically my ST. So this is the formula that I have shown before. This is what I called calligraphic AT. And then this is not really a survival function. So in order to make it a proper survival function, I have to adjust it at infinity. But that's basically the same as saying that, you know, I'm conditioning. If I condition this on the event that the individual actually did get infected, I will get the proper survival function. And this improper, so that probability is computed from the epidemic size equation. So this is very simple, and it basically gives you this really super simple agent-based evolution. So you start with the susceptible individual, and that individual has two choices. Either with probability 1 minus tau, this individual forever remains susceptible, is a survivor, or with probability tau, this individual can move into infection, and that infection will, the timing of that infection will follow the probability of this variable t. And then after exponential amount of time, that individual will move here. The sum of this time and this time is what I call TR, and this is basically just a scaled version again. Both of these quantities F and G, they are described in terms of the trajectories of the initial AD.
I can sort of think of it almost like Brownian particle Brownian motion. You sort of have this fluid of the epidemic around you, which you model deterministically, but my individual trajectory becomes random in this field of the general.
Right, exactly, because you can think about proportion as being a probability, right? So if you're asking a question, what is the probability that this individually random particle ends up being I at some time t, this is basically the approximate. So that's a super simple idea. Oh, go ahead.
Another question. This is really interesting. So I guess based on these marginal laws, you can basically simulate an SIR epidemic by just sampling these independent sets of event times. And so just to give me a little intuition, if you were to have the realization defined by these times, how would it differ? Like, because you did stick in the deterministic limit in here, how would that distribution look compared to just like having simulated via Gillespie?
Yeah, in the large limit, they will look identical. So
yes.
Basically, it will attempt to recapture these curves, right?
Yes, but like what is the how does that distribution approximate? Like what's lost?
Yeah. So I will talk about it in a moment. That's actually that's my talk.
I have an additional question, which is, this is probably a bad model at the beginning of the epidemic. You need sort of the law of large numbers to kick in, which means you need many infected people before you're allowed to replace.
That's exactly right. That's right. So I am basically completely neglecting the stochasticity of this initial infection. If this would start from a single infection, this is a very bad model. So I am assuming that there is a sizable number of infected from the beginning, and that's basically what gives me the lower.
So this is Europe after the flight.
It was Ohio in March or April, when you already knew that there was a sizable number of infected people. So this is definitely that's thank you for that comment. This is what I should have said. So that definitely. So first of all, why is this interesting? It turns out that you can do super simple statistical analyses of all so all of a sudden, think about frailty. as an extension of this, but you know, without frailty, you can just write this, what so statisticians call a likelihood function based of independent random variables. So that's something that in survival analysis people like to do. We understand it a lot. We can use various types of survival models like the proportional hazard, etc. We can basically take all of the existing knowledge and results of survival analysis and now stick it in here with the understanding that this is an approximation. So then the question is, how good of an approximation is it, or is it just an interesting intuition? So, you know, this was one of the things that I wrote down as something that I need to address during the pandemic, and then I didn't have time to look at this. So I did solve it partially, but again, that solution is only for the simplest case. And then in general, I need a general theorem, but at least I will tell you what the intuitions are. So first of all, what I need some kind of baseline. So I will take the Selke construction, but from the individual perspective, and I will think about it as a baseline, and then I will compare it to my approximation. And I will try to measure how these two things differ from each other. So the idea is that I can think of Selke as an agent-based model in the sense that I can basically stick an individual label on every one of the agents in my Selke construction as SIR. I will have this law. An individual agent is, you know, so the Selke construction with individualized agents, it's still a Markov process, right? So I can basically write it in terms of what Etienne doesn't like, which are these Markov processes with rescaled timings. So maybe quickly what these things are. So these will now be binary. So I can write my Markov process in terms of the fate of the single molecule. And the standard way in which I can do this is by means of one way in which I can do this is by means of introducing these rescaled Poisson processes. So this Poisson, this is a unit Poisson process, which is on this rescaled time. And SIs here are zeros or ones.
We choose stop at the first jump, right?
Correct. So it has to stop at first jump because this is on the 0, 1. So as soon as you start, let's say that you are SI, so you start at 1, and then you wait until the first jump. Once the first jump happened, this becomes a 0. So then you shut it. The same here. If you start from I being a 0, then you wait for the first jump, you become a 1, and then eventually you have another jump when you become an R.
But why should the I read only the first line for the moment. Why should the individual I be infected just from those in the sample? That's what I read.
No. They are so these are all individuals, right? So this is the cumulative.
When you sum from j equals 1 to n plus n, and n plus m is your sample, right?
No. This is the entire population, n plus m. So I'm assuming that I have, you know, n plus m individuals in the population. There is no sample here. This is so m is the number of original infections, right? I'm sorry, you know, this is a stitched version of several different talks when I use different notations for different.
So the little n is still total population by constant, right? It's not
correct.
It's total susceptible population at the beginning.
So the point here is that I basically have a way using these rescaled Markov processes of basically representing the Selke construction from the point of view of a single individual in terms of these indicator sets.
Why do you divide beta by n and not by n plus m?
Could have, you know, I could have done it n by n. I'm here. So what it means that I would have to rescale beta in order to recover this. So I'm assuming that m and n are the same one. So basically, I have the following representation. I'm sure that I will be able to explain this. So if you have questions, we can talk about it afterwards. But basically, I am looking at this SI, which basically means that I have an individual who is a susceptible individual, and I am looking at the first jump of this process. Now, if I look at the DSA approximation, the one that I was talking about, what am I doing? I'm basically replacing the rate of infection with the deterministic quantity, right? So it's basically, instead of having a random rate here, I'm replacing this IN with an iota. So I'm keeping the same Markov process. I am just changing the rate from the one that was random to the one which is deterministic. So now I have basically representation of these two processes, which I have on the same probability space, and I can compare them. So I hope that this is obvious, that that's how it works, right? So the other thing which is also interesting here is that then this reveals that this is a very general method, because all I am doing is I am replacing a portion of some stochastic trajectory with a deterministic approximation. And I'm looking at the process that's a result of it. So, you know, this is applicable to potentially a quite wide range of different types of models. Here, it's just useful for SI. So I have, and then that's the punchline, basically. So how do you do this? Now you're in the standard setting. You basically write it up. You write because I'm assuming that things are Markovian here. I'm writing the Grunwald inequality. I am basically checking the exponential inequality for the Poisson process, and I basically borrow that information to look at the difference. So basically, at the end of the day, if I now have my S, which is the true model, so I am counting the number of individuals in my population by time t who are still in S state. And if I look at the same quantity when I'm using this S star, which is obtained from the approximation, then the difference of these two, it's basically of the. So I get an exponential inequality, which I get because of the basically because of the Poisson exponential bound. So you know, the concentration inequality for the Poisson process will give me here the concentration inequality of this.
So if you will try to use that for the more general setting, you probably have to use do, but you will not.
Yes, so we actually have a paper with my friend when we did it in generality, and we used a different concentration inequality. But again, here for SIR,
you don't get exponential concentration.
Under some conditions you do. So you basically need some kind of regularity condition on the process, and you need, in general, law of version of the law of large numbers to hold. As soon as that's true, anyway, yeah, I mean, this exponential inequality is true in this particular setting, but I think it holds for a much larger class of processes in general. It's a very silly trick that I'm using, right? Because I'm basically borrowing that concentration inequality from something else, and then I am just using the Grunwald or something like Grunwald. The key thing is that, you know, I have basically a very simple representation in terms of the scaled Poisson process. So this is useful because what it tells you is that if you run this simulation of mine, which is an approximation, versus if you run the simulation based on just the Selke construction, I actually get convergence quite quickly, as long as my n is large enough. That difference in probability will be small.
But n has to be exponential in t, so this will not work very well.
So t is a finite horizon here. So again, this is my problem with notation. This t now has nothing to do with the random variable t that I was using. It's just
T is the time under which
yeah, right.
But you see that this n is killed by e2 minus nt, so n has to be exponential.
But both L and t is assumed to be a finite time horizon.
Sure.
So
n times t is 100, so we have
yeah. So
100,
obviously
this would be e to the plus 100.
Yeah, obviously. So you know, these are large bounds potentially. But you know, the idea here is that n could be in the order of millions, right? That's the idea. or at least hundreds of thousands. So this should work, and it seemed like, you know, under reasonable conditions, it did. So what does it all mean?
Sorry, can I just, can you go back one slide?
Yes.
So if you think about this capital T, when will S bar and S star bar deviate the most? It will probably not be very, very far away. It will sort of be intermediate values of small t. So nice to get the uniform bound in. I don't see why it should be a problem if you look sort of 10 years future in time or 100 years future in time, they will be more or less the same.
Right. You mean one should be able to found the probability for the soup for all t
Yes.
positive?
It's not very late. I mean, very late. The epidemic is over, so it shouldn't be. I don't know the fine mathematics, but sort of intuitive.
You're right. I mean, there's certainly, again, I haven't spent as much time as I probably should have. This is mostly just to give an idea.
Probably inputted the finite time estimates for law of large numbers.
You have to treat differently the large time, saying that
Right.
both S bar and S bar star are very small anyway.
Yeah. So it could be that you can improve this bound quite a bit by basically following Tom's intuition.
In fact, I believe that you have other bounds like C of t divided by n, which is in theory worse than this one, more practical, and you could take infimum of these two.
So we've done a more subtle version of this in this paper, which hopefully will come out this year at the Journal of Dynamical Systems. So we have a more general, in the Science Journal. We hopefully will be able to explain it. So for instance, this works on SIS models, it works on various other types of models. Setting as soon as you have this representation. So the point here is that it seems like you do get convergence, and this convergence is unique. So what does it mean from the point of view of surveillance, for instance? So it appears that what you can do, you can build these surveillance networks which could operate as follows. You basically randomly select a number of individuals, these honeybee, like they're my sensors, the little humans that basically act as sensors. And you basically follow the status of these individuals. You basically, instead of sampling the entire population for the number of individuals, you just follow these selected ones over time. And you record the timing when these individuals became infected. If you do this, then it basically means that you have a way of converting this entire counting problem into the survival problem, when you're just looking at the timing to infection. Intuition being that if you see lots of these individuals failing more or less at the same time, that means epidemic is grown. When you would see these individuals, you know, failing further and further apart, that means that your epidemic is dissipating. The beauty of this approach is that you don't need to count everybody. In fact, all you need is just a statistical sample out of this large population, because you are interested at the end in these epidemic parameters that are not connected to individuals. So then once you have them estimated, then you can convert it into some kind of estimate for the entire population. But this, at least, you know, in many of the applications that we have used in Ohio, this was a good way on a relatively small samples to get an idea about what's happening. And this was also the one of the methods that we used at the university. So instead of looking at the entire student body, we would just look at the random sample of 50 students and see when they get infected. Fortunately, we were not allowed to use this as our main source of information about COVID. This was more like a useful hobby, you know, so the university was testing all the students. But nevertheless, you know, even from some of these back on the envelope calculations, it seems that this is very efficient in terms of resources and in terms of ability to actually estimate parameters. So all of this is related with these general PDEs that I don't really have time or really intention to discuss. But this is a general PDE model in which you basically build these Selke constructions in a much more general setting, and then you have convergence to the PDE. I think this is a well-known result. I think several of you guys remember these might be your results from some time ago. This is just a general version of the law of large numbers. So what I did, I took a very special form of this beta function here, which basically makes it independent of the susceptible or infected individuals. If I make them just dependent on the susceptible individuals, I get the frailty models. If I make it independent, I would just basically get the usual ODE. But in general, out of these types of PDEs, you can get that statistic. I'm sorry?
What kind of age is S?
So you have T is the time of the system and S is the age of infection. This is kind of like in your model. So you have
infection. I mean, the first term is for susceptible.
The first term is for susceptible. That's right.
People are affected by age of infection.
So they are not, but the point is that you're basically following this additional variable S, for everybody. You can think about it as, once you get infected, you start dynamics on that variable. It's again, this is just a slide to show you that there is a more general structure. I didn't really explain what these things are. So the point here is that you can build the sort of linear PDE model when you have, in addition to the time of on which this an SIR model flows, you also have some other variable.
I'm astonished as him that differentiation by the actual time and differentiation by the sort of time since infection appears so symmetric. You always have dt plus ds.
Not about, but there's a boundary condition.
There's a boundary condition, yes. So this is explained in this paper that we just published. So I would be happy to talk offline about this.
But I think also the different S are different, whether there are arguments of ys or y.
Right.
You have time in each compartment.
Yeah, that's right.
Not the same S.
So this S here is. So yeah. So beta is the rate of infection. So this is the rate at which the individuals are getting infected. So individual of by some time S, individuals of different types are getting infected according to the. Again, I'm sorry, I did not mean to create confusion here. This was mostly meant to be a reminder that there is a more general theory that sort of fits in what I said in a slightly different manner. And what it does, it basically creates these more realistic, potentially more realistic ways in which we can think about epidemics. So for instance, without really changing the overall behavior of an SIR model in terms of the number of compartments, we can see that we can now create this more general models in which, instead of having exponential time to infection and exponential time to recovery, we can actually have any type of distribution that we want to. So for instance, this was Weibull gamma, and the idea here was that we were attempting to make a prediction based on these colored dots over time. So this is from the simulation. And then, the rest of the epidemic was the black curve. If we had enough of the black curve, we were able to almost always very well predict the trajectory. But when we had only a little bit, then it seemed like the exponential, the Markovian model was always over predicting. It was shooting upwards. Whereas these more realistic models were sort of, they were more moderated in the sense that they seemed to get a little bit closer to what actually was the trajectory. And we used some non-Markovian model, but not from the Weibull gamma family. It was, so the point here is that it seems like by building these more extensive types of Selke constructions and using the methodology of the DSA to estimate parameters, you can actually build predictors which are very effective. And doing these human sensors is one way in which you can attempt to understand the dynamics of your epidemic as it's ongoing. And I was very happy to hear from my British colleagues that they're basically using this idea in England now, or in Great Britain, because they have contracted with the number of households across the country, and they're checking periodically on these households in terms of the numbers of infections, and that in fact they're using this thing as sort of monitoring system for the entire country in terms of different types of symptoms and different types of diseases. But the key point is that this is the same household over and over and over. So they're basically longitudinally following these different households.
So they do the random sampling once forever.
That's right. At least for a period of time. That's right. No, so you do functional sampling based. That's exactly right. So I will skip this. So I just want to say one thing. These models are very flexible and they're potentially usable in various different circumstances. We have most recently used it on some data from environmental sampling, where the idea was that we had some measurements of water and we had some measurements of seroprevalence, and we wanted to see basically what is the actual prevalence. So these types of models can be adjusted. They can be adjusted into adding additional pieces to it, and then they can be used. What this picture is meant to show is that these models, at least in the simple examples that we have used, seem to work. This was an example when we estimated sort of the prevalence of infection in one county in Kentucky, and this is the information from the wastewater. So you can basically see that these two curves kind of look similar. They're on the same picture, but they're not related. But the point is that you have some kind of dynamics of these things that seem to be making sense. And this is another example when we looked at tracking some of these things with seroprevalence. So the idea is that there's many potential applications in different aspects of monitoring of these kinds of DSA methods. And what the DSA does, it makes all of this possible statistically. So I think this is all I wanted to say. The really important aspects are here. So these are my two wonderful collaborators, Wasur and Eben. You guys know both of them. They've been involved in various stages of this and certainly worked with me on the Ohio COVID project. And I would like to thank NSF for helping us fund this. Thank you for your attention.
Thank you very much. Sorry for interrupting you all the time, but I think it's very nice to have these discussions actually during the presentation, so I don't mind that. At least I don't. I'm not the organizer. Are there more questions? Yes, Christian.
So I have a question. We had this discussion whether we underestimate the number of cases by a factor 10, 100 or 1,000. And do your methods, can you comment on that? Maybe your method, since you sort of have this nice picture, maybe you can tell us whether it's 100 or 1,000.
So I don't have this picture here, but because this is just from the wastewater, but I have a picture when I think that in this particular data set, so just a little bit of background. This was from the 2021 in Kentucky, in this one big county around the city that's called Louisville. It's about 1 million people. They did an extensive testing of water and also extensive testing of seroprevalence. So they were basically measuring how many people had COVID. This was a random sample. And then they compare it to water. In that particular analysis, once we looked at the water samples and once we looked at our estimates, I think there was about 40% difference in terms of what was reported versus what was predicted by our model.
So you don't think it's a factor 100 as we were discussing?
No.
Or
I mean,
factor
at least
10 for the world population?
So I don't know how this would work for the world, but at least in Jefferson County, Kentucky, this was maybe half, you know. And this was based on the water samples, so not just on the counts based on the models, but it was really based on the amount of virus that was floating in the sewer.
Yeah, well, that's great to see, actually, the correlation between.
Right. So we wrote like a really, I think, a paper claiming that we have a wonderful regression that allows you to regress.
These, you can use that as a predictor next time to do some kind of genomic, well, no, not even genomic surveillance to determine that there's already an outbreak going on in the population.
Correct.
Even when the CDC is not aware of it, by just monitoring what's happening in the sewage system.
So this is a very nice feature of these types of models, that you can actually map it to something that's measurable in.
I want your model, your way of estimating also seems to work right well, and that you could use even if you don't have wastewater.
Correct.
And then you could estimate for the whole US maybe what the factor is.
Correct. And again, we would, so we have done some of this. We try to stay away from these various competitions that were run by different people, mostly because we were so busy trying to fit these models to Ohio that we didn't do it in more generality, but it's possible. When we compared our methods of estimation and the results from it to the official statistics from that county in Kentucky, that the difference was about 40%. And I have a picture, but not here. So I would need to look for it. I can show you.
So I think in general, it's a very hard question to, from the reported cases, to say anything about what fraction are unreported. I think it's an identifiability issue.
Right.
Jason raises his hand and probably has comment on that as well. We discussed this briefly yesterday.
Yeah, well, that's not what my comment is about, but that's a fascinating question too. So first of all, this is a beautiful talk. I love it. Quick question about, so you have really nice results that, like you said, allow you to simulate essentially without really simulating like POMP. But when you fit data like this, for instance, like you have access to Hamiltonian MCMC, and I know that you had a really nice likelihood expression. And so you can take gradients, it's exponential family. But when you have data like this, I guess, is there like an amount of missing data that your method also helps you impute, or do you not deal with that? Do you not encounter that?
So I don't. So the beautiful thing about survival model is that I actually don't have to worry. So if I have data which says that, you know, I have some kind of censoring or I have interval censoring, which I almost always do, I can incorporate this, right? Because I can just say, I know what is the probability that that individual got infected between that time and that time. We have used this quite a bit, for instance, when we're doing initially surveillance of prisons in Ohio, when we had limited amount of testing of prisoners, but we were, so basically we had censoring, right? We knew that the infection must have occurred earlier, but we didn't know exactly when. But you can put it into this likelihood function. That's the advantage of using survival models. So no, so that's basically also what I'm saying here. So this is kind of an alternative to process reconstruction.
Right. So instead of like imputing the missing data, it just becomes converted to like sensor times tails of survival function. That's awesome.
So you basically make it simpler in this way.
Any?
The Kentucky data.
Sorry.
So the Kentucky data, the Louisville, your model overestimated the reported cases, right? That's what happened, or 40%?
Our model, again,
which would be correct if you, I think, if you'd overestimated, because
let me see if I have a way of
of
showing the picture, because maybe
Oh, okay.
It was not a very important one. Let me try to show you, right?
Okay.
So idea was as follows. This data was fitted. So I took the method that we had. So this method can be applied to various types of data. It can be applied to incidence data, which is typically what you would observe from the epidemic curve. It would be applied to prevalence, except that most of the time you don't know what the prevalence is. So you don't, but you can apply it to seroprevalence, which is a little bit better way of measuring the past infection. So here we applied it to incidence data in that county. This was the fit of the model. And this was the data, the way that it was given to us. And then based on that, we have calculated prevalence over time. So we, from this incident rate, we have computed the prevalence, which was this red curve over here. And on top of this, we put the prevalence that we calculated based on our method and based on the seroprevalence sampling that was done in the population. There were some problems with the seroprevalence sampling because there was a low response rate and there were some biases. So again, this is not ideal, but it was definitely better than what was in terms of the overall picture of the community infection. It was, I think, a more reasonable approach. And we did it over time. So we had these samples that we're collecting like this. This is a number of positive tests, and we did in July, October, January, and I think March. So this is kind of how it looked like in terms of the number of people and the percentage of positive tests. These were all reasonably good tests in the sense that they were that they had pretty high sensitivity and specificity, but we adjusted. This is not difficult to do. And then based on these curves, this is seroprevalence. So based on these curves, we computed prevalence, which kind of looked like this, and that gave us also a way of comparing this with the prevalence from the data that was publicly available. So if the red curve is the data that was available from the Jefferson County public health side, then the black one is the one that sort of comes out of the prevalence estimates that we have computed.
So it's a 40% difference? Or?
Yeah, it's a little bit more, so for a while it was more or less the same or very similar, and then it diverted quite a bit.
I think we end for this. We can continue discussion, but it's time for coffee, and we reconvene at 11 o'clock if Joel Miller has arrived by then. Otherwise, it's a longer break.
Well, yeah, I need to mention, because he may not be here physically, he may be presented from his hotel room. He's a little under the weather, so I'm trying to. Yeah, so it's possible, or we may get Greg to continue talking for another hour.
Now break.
Right now, yeah.
I'm not sure if you would like that, but thank you very much for the.